This honors geometry lesson is on the Isosceles triangle theorem, Chapter 3, Section 4. The objectives are to learn and apply theorems and corollaries involving an isosceles triangle. Recall that an isosceles triangle has two congruent sides. These congruent sides are called legs, and the third side is called the base. The angles at the base are called base angles, and the angle opposite the base is called the vertex angle of the isosceles triangle. Let's take a look at the isosceles triangle theorem, which states if two sides of a triangle are congruent, then the angles opposite those sides are congruent as well. Let's go ahead and prove this. What we're going to do first is we are actually going to bisect angle A. Remember that a bisector cuts the angle into two congruent parts. So if we bisect angle A, and what we're going to do is where the bisector intersects B and C, we're going to call that point D. So what we know is that a bisector will cut the angle into two congruent parts. So now we know that angle BAD is congruent to angle CAD. The next thing we know is based on the reflexive property that segment AD, since it's shared in both triangles, can be equal to itself, using again that reflexive property. So as you can tell, we now know that triangle BAD is going to be congruent to triangle CAD based on the side angle side postulate. Once we know that the triangles are congruent based on SAS, we can then use CPCTC, which states that corresponding parts of congruent triangles are congruent, which allows me to now mark that angle B must be congruent to angle C. And as you can tell, if AB is congruent to AC, so if two sides of a triangle are congruent, then the angles opposite those sides are congruent as well. And as you can tell, B and C are opposite side AC and side AB. Let's go ahead and take a look at the converse of the isosceles triangle theorem. The converse is the opposite, or working backwards. So the converse of the isosceles triangle theorem states if two angles of a triangle are congruent, then the sides opposite those angles are congruent as well. So let's go ahead and bisect angle A one more time. And where it bisects, we're also going to call that point D. And we're going to mark that angle BAD is congruent to angle CAD based on that definition of an angle bisector. Now what we're going to do now is we're also going to indicate that AD is shared by both triangles, so using that reflexive property, we can also say that AD is congruent to itself. So I want you to go ahead and take a look at the markings. So based on these markings, I don't have side, side, side. I don't have side, angle, side, and I really at this point can't see that I have angle, angle, side. So what we're going to have to do is go back to what we learned in previous chapters. So we know if two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent as well. So what this tells me, since B is congruent to C, and angle BAD is congruent to angle CAD, then now I know that angle BDA must be congruent to angle CDA. So now I can go ahead and I can mark this. So now if you take a look again at the triangles, you can now say that triangle BAD is congruent to triangle CAD based on angle, side angle. Once we know that, we now know that side AB is going to be congruent to side AC based on CPCTC. So now we can tell that if two angles of a triangle are congruent, so we started off with angle B is congruent to angle C, then the sides opposite those angles are congruent as well. And now we were able to prove that segment AB is now congruent to segment AC, which are the sides opposite angle B and C. So now that we review the theorems for isosceles triangle, let's review some corollaries that are going to help us solve the next couple examples. So we know an equilateral triangle is also equiangular. Each angle of an equilateral triangle must measure 60 degrees. The bisector of the vertex angle of an isosceles triangle is perpendicular, or is a perpendicular bisector of the base. So if you look at the two previous examples, when we bisected angle A, you can see that it intersects the base at a 90-degree angle, therefore making it perpendicular. And lastly, an equiangular triangle is also equilateral. So let's take a look at example 1. We're going to find the value of x in the triangle. if you go back to the converse of the isosceles triangle theorem, which states if two angles of a triangle are congruent, then the sides opposite those angles are congruent as well, this is going to help us solve for x. So what we know is that we have two angles that are congruent, so therefore the sides opposite must be congruent as well. So I know that this side and this side are going to be congruent because the angles opposite them are congruent as well. So we know that one side equals 2x minus 4, and that the other side equals x plus 2. So remember, if the angles are equal, then the sides are equal. So now we have an equation that is going to allow us to solve for x. So if we subtract x from this side, we're going to have x minus 4 equals 2. And if we add 4 to both sides, we are going to see that x equals 6. Now what we can do is we can actually go in and we can check our work. So if we substitute in 6 for x, we have 6 plus 2, which gives me a side length of 8. And also down here, if we substitute in 6 and we solve our expression, 12 minus 4 also gives us a side length of 8. Therefore, x must equal 6 in order for the sides opposite those two congruent angles to also be congruent as well. For the last example, we're also going to find x in the triangle, but this time we're going to go and look back at the isosceles triangle theorem, which states if two sides of a triangle are congruent, then the angles opposite those sides are congruent as well. So for this case, what I'm going to do is I'm going to mark the angles opposite the congruent sides that must be congruent to each other. Okay, so I want you to notice that the angle right here must be congruent to the angle up here. So if the angle up top has the expression x squared plus 2x, then the angle down here must also carry the same expression of x squared plus 2x. So we're going to go back to our triangle sum theorem, which states that all three angles of a triangle must add up to 180 degrees. So I'm going to take my first angle, which is x squared plus 2x, add it to my second angle, which happens to also be x squared plus 2x, since they are congruent, plus this angle down here, which is 132 degrees, and I know together that must equal 180 degrees. So now what we're going to do is we're going to go back to what we learned in Algebra 1, and we're going to solve for x. The first thing I want to do is combine all my like terms. So I know that x squared plus x squared is 2x squared, and that 2x plus 2x is 4x. I'm going to carry down my 132 equals 180. The next thing I'm going to do is I know that I'm going to have to factor because I have a quadratic. So in order to factor, remember the right-hand side of the equation must equal 0. So I'm going to move the 180 degrees over, which leaves me with 2x squared plus 4x minus, let me put the minus there, so 132 minus 180 is a negative 48. Is equal to 0. Now remember, before you factor a quadratic, you want to make sure that you factored out any greatest common factors. So if you look at 2x squared, 4x, and negative 48, you can see that the greatest common factor is 2. So the first thing I'm going to do before I start factoring my quadratic is to go ahead and factor out the GCF. So this leaves me with x squared plus 2x minus 24 is equal to 0. Now what I'm looking for is I'm looking for two numbers that multiply to negative 24 and add to 2. So two numbers that multiply to negative 24 and add to 2. So that is going to be a positive 6 and a negative 4. So I'm going to have x plus 6 times the quantity of x minus 4. Okay. So now we've completely factored our quadratic. Now we just have to solve for x. So remember, when you solve, you're going to take each expression for each factor and set that equal to 0. So on this side, I know that x could equal negative 6, or on this side, x could equal a positive 4. So my solutions for x are a negative 6 and a positive 4. If you are not sure whether or not you did this correctly, you can go ahead and substitute in negative 6 and 4 into x and see if it actually equals 180 when you add all three angles. Or you could actually plug in x for each expression and see if the two angles, not the 132, but the two other angles, are equal to themselves. So let's go ahead and do that. So we're going to start with negative 6. So negative 6 squared is 36, and then 2 times negative 6 is a negative 12. So 36 minus 12 is 24. So if I solved correctly, the angle down here is also going to carry a value of 24. And we know that x squared plus 2x is, when I plug in x, is 36 minus 12, or 24. And then if I use what I know about the triangle sum theorem, if I take 132 plus 24 plus another 24, that does give me 180 degrees. Now we also want to make sure that we test both the x values. So let's go ahead this time and we're going to go ahead and plug in 4 for x. Okay, so x squared plus 2x, so 4 squared is 16, plus 2 times 4 is 8, and you can see that 16 plus 8 is also 24. And then if I substitute in for the bottom as well, since it carries the same expression, 4 squared is 16, and 2 times 4 is 8, which also gives me 24. So if we go back to our triangle sum theorem over here, we're going to get that 132 plus 24 plus 24 is 180 degrees. This concludes the lesson on the isosceles triangle theorem. If you have any questions, feel free to watch the lesson again. After watching it for a second time, if you still have questions, please write down your questions and see me in class.